So it was something like this. The pith ball was really high. So what you did is they touched the pith ball with the charge of the plate, and then the plate was like something like this. So we could actually calculate. Let's see here. We could say, what's the electric field created by the plate? And then we could solve for the Q, the charge of the pith ball. And then the angle here was quite high, like something like, let's say, 70 degrees. So let's estimate what the mass of the ball is. Let's say the mass of the ball is 100 grams. So let's first calculate what the electric field. What is the electric field created by the plate? So what's the definition? So far I've talked about electric force, right? Is KQ over R squared. So what's the definition of electric field? Electric field. Electric field is electric force divided by Q. So the units of electric field would be Newton per Coulomb. In other words, even if this charge Q is not there, this plate that is charged, let's say there's positive charge on this plate, right? That charge creates an electric field. So there doesn't need to be any charge here for this guy to create an electric field. You see, this guy will create an electric field. It's almost like the question, if a tree falls in the forest and there's no one there to hear it, does it make a sound? You know, that philosophical question. And people like wonder, okay, does it make a sound? Well, there's no one there to appreciate the sound, right? And so they kind of get twisted up with that question. And doesn't matter. And my answer to that is, it doesn't matter if there's no one there to pick up the sound or appreciate the sound, right? The tree falling in the forest will create a sound wave with a certain field, you know, with a certain energy and certain power, right? That will propagate through the air. So of course it will make a sound. If everybody's dead in the world, it will make a sound. Just there's nobody there to appreciate it. So if you have a charged plate, it will make an electric field, irrespective of if there's another charge to appreciate that or not. You see? You guys agree with me? The falling tree will make a sound? Maybe it's better to say it will make a sound wave. It will make a sound, feels like, you know, something like that. You need someone to say, oh, that's a sound wave. Of course, yeah, you need someone to appreciate that. But it will make a sound wave, you see. And then once there is somebody, then they will experience that sound, because the pressure will go, the sound wave will go into their eardrums and vibrate their eardrums. And then that person will say, oh, a tree fell, you know. So in other words, the electric field is that same idea, is you're taking the force that the charge would have experienced if it was there, and then you're dividing it by the charge of that charge. And you're saying, let me divide out the charge and say, what's the electric field created by this? So in this case, then, what is the electrical field? If I divide this by one of the Q's, what's the electrical field created by a point charge? Then it'll just be KQ over R squared. You see, so this is a general equation that tells us electric field has units of Newton per Coulomb, right? And then this works if the plate was a point charge. If the plate is a point charge, then the electric field created by it is KQ over R squared. But if it's a plate, the equation is different, okay? So we're gonna get into that in the next chapter, is what is the electric field created by, well, actually, we'll get into it this chapter too, yeah. What is the electric field created by plates? You see. So, therefore, if I want to know what is the electric field created by the plate, let me analyze the forces on this charge now. I have the charge, so I have the tension on the charge, T, like that. The tension in the string is pulling it that way. Then I have the weight of the charge, right, which is mg. Now, if the charge that I have here is positive, if the charge that I have,
wouldn't it have to be negative because it's being attracted to the
yeah, because it has to be tracked. In the video, I think what they did was first rub it against something, then touch this, then they brought the plate. And so the plate must have had an opposite charge of that. So this must be negative. Because if you touch this with positive, and then you bring a positive, it's going to push it, and then the thing is going to swing the other way, you know? So they first have to come and charge it with a negative charge, right? So let's say this is negative. And then the electric field is this way. So then what's going to happen? This guy is going to feel negative charges experience a force opposite to the direction of the electrical field. So they get attracted towards the electric field. So the force of it is going to be like this, the electric force. So the electric force that it feels is going to be what? Q times the electrical field created by the plate. You see? So if I want to know the electrical field, if I want to know the force felt by a point charge, then I just multiply the charge of that charge, Q, times the electrical field. So if the electrical field is to the left, that charge, if it's negative, it's going to feel a force to the right. Then I'm going to divide this tension into X and Y components, right? So if this is 70, then that means that angle is going to be 20. So then this component right here is going to be T cosine 20. And then that component is going to be T sine of 20. Right? And then, so therefore, in order for the charge to stay in equilibrium, we say T sine of 20 must equal, this guy must equal to the mg, right? So that they balance out. And then T cosine 20 must equal to the force right here, which is QE. So given, in other words, given the angle from the experiment, if we could measure that angle, then we can just say, break that up into components, and then one of the components is equal to the weight, and then the other component is equal to, okay, so now we divide this, and then we get tangent of 20, sine over cosine is tangent, is equal to mg over QE. Okay, so either in this case, if the electrical field is given to us, I mean, if they're asking for the electrical field, then the problem would have to give us the Q. Yeah, one of them would have to be given. So M has to be given, and then one of these has to be given. So let's say the Q is 1. More likely it's very small, so it's probably be something like 1 microcoulomb, let's say. Okay, so then if we know the charge is 1 microcoulomb, we can solve for the electrical field. So E is mg over Q times tangent 20. So cross multiply here. Okay, so let's write it here. E is equal to mass. We were told is 100 grams. So convert that to kilogram, 0.1 kilogram. Then G is going to be 9.8. Divided by Q, if that's given as 1 microcoulomb. So then we just put 10 to the minus 6. Remember, micro was a 10 to the minus 6 up here. 10 to the minus 6. Okay, so then 0.1, 9.8, 10 to the minus 6, and then tangent 20. Okay, let's put that all in and see what kind of number we get. .1 times 9.8 divided by 20 tangent. Wait, 20 tangent shouldn't be that small. 20 tangent, no. 90 tangent. Yeah, I see, I'm probably in radian mode. My alarms always go off when something doesn't work. So you go degree, 90 tangent, error. Yeah. So that's kind of how you test to see if you're in degree mode. If you take tangent of 90 degrees, it should be infinity. So it shouldn't exist, you see? Okay, so then, so this was a 0.1 times 9.8 divided by 20 tangent. Okay. Okay, so then you have E. The 10 to the minus 6 will go up to the top. So then E will be really large E. 2.693. And then the 10 to the minus 6 will go up to the top and we'll make it 10 to the 6 Newton per Coulomb. Wow. So that's 2.693 mega Newton per Coulomb. Mega, 10 to the 6th. That's pretty strong electric field. And that's if it's 1 micro, if the charge was 1 micro. If it was 1 nano, then the electric field will even be stronger. It could be maybe a millicoulomb. Okay, so the second question can be, what is the charge on the plate? So what is the total charge on the plate? So then we have to find out what is the electrical field created by a plate. So I'm kind of jumping ahead to the topic, but we're going to eventually get to that. Electric field of plates. It's sigma over 2E0, where sigma is the charge density on that plate. Okay, so the electric field of a plate, so they use the paper plate in that example. So the electrical field created by the paper plate is going to be sigma. Sigma is how much charge it has divided by its area, divided by 2E0. Okay. Okay, let's stop there for a second. So sigma divided by 2E0. So that means the electrical field would be sigma over 2E0, and then sigma is defined as the charge on the plate divided by the area of the plate. Right, and then let's find out what the number E0 is. The number E0 is called electrical permittivity of free space. E0. So it's commonly called the vacuum permittivity of free space, or electrical constant, or the distributed capacitance of the vacuum, is an ideal constant, which is the value of the absolute dielectric permittivity of classical vacuum. In other words, it tells you it is the capability of an electric field to permeate into a vacuum. So in other words, think of it this way. The more common, ordinary language way of saying it is that E0 tells you how well vacuum space conducts electricity. Right? That's kind of what E0 is. How well vacuum allows electricity to flow through it, or the other way to say, electrical fields to flow through it. You see? And then if you do 1 over 4 pi E0, that gives you K, the 9 times 10 to the 9th, the Coulomb's constant. So Coulomb's constant is just simply 1 over 4 pi E0. So E0 itself is 8.854 times 10 to the minus 12, 8.854. So it's kind of a more repeating decimal, times 10 to the minus 12. Okay, so then, if I want to find the charge of the plate, I'm going to have to put all of these together. So the electrical field of the plate is 2.693 times 10 to the 6th. And then the Q over 2. And then E0 is 8.850 times 10 to the minus 12. 8.85 times 10 to the minus 12. That's the E0 number. Okay, times the area of the plate. So what's the surface area of a paper plate? Pi r squared, right? What was the radius of the plate, of a typical paper plate? Maybe about 10 centimeters. Yeah, that sounds about right. So 0.1 meters. So in that demonstration, we have pi, and then that's the area of the plate. So remember, sigma is the surface density, charge density. So it's the charge divided by the area. So then pi times the radius squared, the E0 number, the 2. Take all of this over there. Okay, so now 2.69 times 10 to the power 6. So that's the electrical field, okay, times 2 times 8.85 times 10 to the power 12 negative times pi times 0.1 squared. Okay, so the charge is going to be, so if we go back here, 1, 2, 3, 4, 5, 6. Yeah. 3. Let's see. 1, 2, 3, 4, 5, 6. 1.497 times 10 to the minus 6. Let's see if our answers are realistic. What did we assume was the charge of the, what did we assume was the charge of the other one? The charge, 1 microcoulomb. We assume this is the charge of the 1 microcoulomb, and this is also micro. The plate has a charge. Those are very realistic numbers. In other words, I wanted to see if this was 1 microcoulomb, and this was a similar charge to that, of the same order of magnitude. So it came out to be 1.5 microcoulomb. So if this is 1 microcoulomb and 1.5 microcoulomb, this would produce enough strong of a electric field to attract that to the point where it would rise 70 degrees. Wow, it worked out. It's kind of weird that the electrical field created by a 1.5 microcoulomb plate, right? The electrical field is that strong, 2.7 mega Newton per Coulomb. You see, because this is micro, the area is small, right? And plus the E0 is very small, 10 to the minus 12. So you don't need a lot of charge to create a huge electrical field. To have, in other words, for this guy to really attract this very noticeably, you don't need very strong charges. A microcoulomb is already large enough. Cool, it worked out. So just from that, we learned that the charge of the pith ball was around 1, something like that. And then this was a little bit stronger, the plate. And then that creates the situation that we saw in the video. Okay. Now let's go to the 2 pith ball problem that we saw, the video that we saw.